In this chapter, we discuss data warehousing and business intelligence. Let's start with the introduction. Until this point, we have largely focused on storing data in the most optimal way, ensuring its integrity as much as possible at all times. The next obvious question is what we can do with this data from a business perspective. In this chapter, we discuss how to take data and extract valuable new business insights from it. Here you can see its outline. We start by zooming into the various levels of corporate decision-making and how this relates to data requirements that support these decisions. This will bring us to the concept of a data warehouse, a massive consolidated data store which we formally define and extensively discuss in terms of data model or scheme, design, and development. We contrast data warehousing with some newer developments such as data marts, virtualization, operational data stores, data lakes, and indicate synergies. We then zoom into business intelligence, or BI, discussing query and reporting, pivot tables, and on-line analytical processing, or OLAP, as key techniques to better understand and unravel hidden patterns in your corporate data. Each company has different levels of decision-making, which have an important impact on the underlying supporting data infrastructure. The first is the operational level, where day-to-day business decisions are made typically in real time or within a short time frame. Traditional databases were primarily developed for these operational decisions and have a strong transactional focus in which many transactions need to be processed in small units of time. Think of a point of sale or POS application storing information about who buys what products in what store at what time, or a banking application processing daily money transfers. Given the strong focus on managing transactions, these systems are also commonly described as online transaction processing or OLTP systems. The next level of decision-making is the tactical level, where decisions are made by middle management with a medium-term focus, for example, a month, a quarter, or a year. As an example, think of a store manager who wants to know the monthly sales for all products to decide upon replenishment orders. Finally, at the strategic level, decisions are made by senior management with long-term implications, for example, 1, 2, 5 years or more. As an example, think about the chief executive officer who wants to inspect the geographical distribution of sales in order to make an investment decision about building a new store. Operational systems focus on simple insert, update, delete, and/or select statements and consider transaction throughput as one of the most important KPIs. The information systems needed at both the tactical and strategic level are often referred to as decision support systems, DSSs, since their primary aim is to provide information to support decisions either in the mid or long term. Those DSSs require other types of data manipulation than traditional operational systems. More specifically, DSSs focus on data retrieval by answering complex ad hoc queries or select statements in a user-friendly way. They should include facilities to represent data in a multidimensional way, support various levels of data aggregation or summarization, and provide interactive facilities for advanced data analysis. A DSS should also provide support for trend analysis by detecting patterns in a time series of data. Hence, given these different requirements in terms of data storage and manipulation, a new type of comprehensive data storage facility is needed to implement a DSS. A data warehouse provides the centralized, consolidated data platform by integrating data from different sources and in different formats. As such, it provides a separate and dedicated environment for both tactical and strategic decision-making. A data warehouse was first formally defined by Bill Inman already in 1996 as follows. A data warehouse is a subject-oriented, integrated, time-variant, and non-volatile collection of data in support of management's decision-making process. Subject-oriented implies that the data is organized around subjects such as customers, products, sales, etc. By focusing on the subjects rather than on the applications or transactions, the data warehouse is optimized to facilitate the analysis of the decision makers by leaving out any data that is not relevant to the decision-making process. The data warehouse is integrated in the sense that it integrates data from a variety of operational sources and a variety of formats such as RDBMSs, legacy DBMSs, flat files, HTML files, XML files, etc. To successfully merge and consolidate all this data, the data warehouse needs to ensure that all data is named, transformed, and represented in a similar way. Non-volatile implies that the data is primarily read-only and will thus not be frequently updated or deleted over time. Hence, the two most important types of data manipulation operations for a data warehouse are data loading and data retrieval. Time variant refers to the fact that the data warehouse essentially stores a time series of periodic snapshots. Operational data is always up to date and represents the most recent state of the data elements, whereas a data warehouse is not necessarily up to date, but represents the state at some specific moments in time. This table summarizes the key differences between a transactional system and a data warehouse. A transactional system focuses on day-to-day business operations, whereas a data warehouse focuses on decision support at the tactical and strategic level. In terms of data latency, a transactional system works with real-time data, whereas a data warehouse uses periodic snapshots, including historical data. Transactional systems are typically based on an application-oriented design, whereas a data warehouse is subject-oriented. In terms of normalization, a transactional system works with normalized data, whereas a data warehouse can sometimes also have denormalized data for performance reasons. A transactional system works with insert, update, delete, and select operations, whereas a data warehouse only focuses on insert and select operations. Transaction management is important for transactional systems, but less of a concern for a data warehouse, since data is mostly retrieved. Finally, a transactional system processes many simple queries, whereas a data warehouse processes fewer but complex and ad hoc queries. Various conceptual data models or schemes can be adopted to design a data warehouse, which all involve the modeling of facts as well as dimensions with which to analyze these facts. In what follows, we discuss the most common schemes: a star scheme, a snowflake scheme, and a fact constellation scheme. We also zoom in on some specific scheme issues. As the name suggests, a star scheme has one large central fact table which is connected to various smaller dimension tables. As illustrated in this figure, the fact table has multiple foreign keys referring to each of the dimension tables, implementing a one-to-n relationship type. The primary key of the fact table consists of the composition of all these foreign keys. The fact table typically contains a tuple per transaction or event and also contains measurement data such as sales in units and sales in euros in our example. A dimension table stores further information about each of the facts in the fact table such as time, store, customer, or product. Additive measures can be summarized along all dimensions using addition operators such as sum, average, etc. These are the most common type of measures encountered. In our example, sales in units and sales in euros can be meaningfully added across the time, store, product, and customer dimension. For example, we can look at sales per month, average sales per customer, etc. The dimension tables contain the criteria for aggregating the measurement data and will thus be used as constraints to answer queries such as what are the maximum sales during a particular quarter across all products, stores, and customers? What are the average sales per customer across all time periods, stores, and products? What is the minimum amount of units sold in store XYZ during quarter 2 across all products? To speed up report generation and avoid time-consuming joins, the dimension tables often contain denormalized data. In other words, the dimensional hierarchies, for example day, month, quarter, year, and therefore transitive dependencies are less clear from the design since they are collapsed into one table and hidden in the columns. Since these dimensional tables are only seldom updated, we don't have to worry too much about the risk of inconsistent data. Here you can see some example tuples for our star scheme. It can be seen that for his birthday, on February 27th, Bart with customer key equal to 2000608 and customer number 20 bought 12 bottles of Jacques Solas Brut Initial 2012 with product key 30 and product number 0199 in Vinos del Mundo with store key equals 150 and store number 69. A Snowflake scheme normalizes the dimension tables as you can see illustrated here. By doing so, it essentially decomposes the hierarchical structure of each dimension. This creates more tables and primary foreign key relationships, which may have a negative impact on report generation due to the many joins that need to be evaluated. A Snowflake scheme might be considered if the dimension tables grow too large and a more efficient usage of storage capacity is required. It may also be beneficial if it turns out that most queries don't make use of the outer level dimension tables, for example the category dimension, segment dimension, and only need access to the dimension tables directly connected to the fact table, for example the product dimension and customer dimension. A fact constellation scheme has more than one fact table, as you can see illustrated here. The two fact tables, sales fact table and shipper fact table, share the dimension tables, time dimension, product dimension, and store dimension. This scheme is sometimes also referred to as a collection of star schemes or a galaxy scheme. In this section, we elaborate on some specific scheme issues. We discuss the use of surrogate keys and the granularity of the fact table. We introduce factless fact tables and give recommendations to optimize the dimension tables. We define junk dimensions and Outrigger tables. We conclude with guidelines on dealing with slowly and rapidly changing dimensions. As you may have seen in our examples above, many of the dimension tables introduce new keys called surrogate keys, such as store key, product key, shipper key, etc. These are typically meaningless integers used to connect the fact to the dimension tables. An obvious question is why we cannot simply reuse our existing natural or business keys, such as store number, product number, ship number instead. There are various reasons for this. First, business keys usually have a business meaning in the OLTP system, such as Social Security number for employee and VAT number for company. Hence, they are tied to the business setting and requirements, and if these would change, for example due to a merger or acquisition or a new legislation, then all tables using those keys need to be updated, which may be a resource-intensive operation in a data warehouse environment because not only the current state is stored, but also historical data. Surrogate keys essentially buffer the data warehouse from the operational environment by making it immune to any operational changes. They are used to relate the facts in the fact table to the appropriate rows in the dimension tables, with the business keys only occurring in the much smaller dimension tables to keep the link with the identifiers in the operational systems. Furthermore, when compared to surrogate keys, business keys are usually bigger in size, which will result in big indexes and slow down index traversal and consequently query execution time. Therefore, using surrogate keys will save space and improve performance. This is especially true for the fact table since most of its attribute types are foreign keys. Next, business keys are also often reused over longer periods of time. Hence, they cannot be used as primary keys in a data warehouse storing multiple snapshots of the data across longer time periods. Finally, surrogate keys can also be successfully used to deal with slowly changing dimensions as we discussed below. Since the fact table contains the bulk of the data, it is important to design it at the appropriate level of granularity or grain. In other words, you should think carefully about the semantics in terms of the level of detail of one row of the fact table. A higher granularity implies more rows in the fact. A higher granularity implies more rows in the table, while a lower granularity implies fewer rows. When determining the granularity, a trade-off between the level of detailed analysis supported and the storage requirements, and hence query performance, needed should be evaluated. Note that it is always possible to obtain a lower granularity from data stored with a higher granularity, for example going from days to months, by using aggregation. Obviously, if data is stored at a lower granularity, for example monthly, it is not possible to obtain more detailed information, for example daily. Examples of grain definitions could be: one tuple of the fact table corresponds to one line on a purchase order, or one tuple of the fact table corresponds to one purchase order, or one tuple of the fact table corresponds to all purchase orders made by a customer. A factless fact table is a fact table that contains only foreign keys and no measurement data. Although it is less common, it can be used to track events. Here you can see an example for a course administration. The fact table records the attendance of a student for a course taught by a professor at a specific moment in time. This data warehouse design allows you to answer questions such as: which professor teaches the highest number of courses? What is the average number of students that attend a course? Which course has the maximum number of students? A dimension table usually has a smaller number of rows compared to the fact table. The number of columns can get quite large, with many of them containing descriptive text. To improve query execution time, the dimension tables should be heavily indexed because they contain the information that will be used as selection criteria. On average, the number of dimension tables is between 5 and 10. A popular dimension table is time, which is included in almost every data warehouse. It can be easily built up front. Here you can see an example of the time dimension definition. As you can see, it contains a lot of date attribute types such as information about day of week, day of month, fiscal periods, holidays, etc. An interesting question is how to deal with low cardinality attribute types such as flags or indicators. Consider the attribute types online purchase, yes or no, payment, cash or credit card, and discount, yes or no. We can either add these attribute types directly to the fact table or model them as 3 separate dimensions. Another interesting alternative might be to combine them into a junk dimension, which is a dimension that simply enumerates all feasible combinations of values of the low cardinality attribute types as shown here. Note that although 2 to the power 3 or 8 combinations are theoretically possible, we left out the 2 impossible ones with online purchase equals yes and payment equals cash, leaving us with 6 feasible combinations. We also introduced a new surrogate key, junk key 1, to link this junk dimension table to the fact table. An Outrigger table can be defined to store a set of attribute types of a dimension table which are highly correlated, low in cardinality, and updated simultaneously. As an example, suppose we have a customer dimension table which also includes demographic data obtained from an external data provider. More specifically, attribute types are provided on a monthly basis such as average income, average household size, unemployment rate, percentage female population, percentage home ownership, etc. in the geographical region where the customer lives. If we would keep this information in the customer dimension table, it would imply a lot of duplication of information and consequently heavy data manipulation in case of updates. A more attractive alternative is to put this information in a new table, an Outrigger table, and link it through a foreign key with the customer table as you can see illustrated here. It is important to note that this Outrigger table is not directly connected to the fact table. An advantage of this approach is that the customer dimension table now has fewer attribute types and the Outrigger table has a relatively small amount of rows since the demographic data is now only stored once per region instead of once per customer. A drawback is that an extra join is needed to combine both tables. Although a view can be defined to facilitate this, it is recommended to be careful and not define too many Outrigger tables in your data warehouse design. As the term suggests, a slowly changing dimension is a dimension that changes slowly and irregularly over a period of time. As an example, think of a dimension table customer that has an attribute type customer segment ranging from AAA, AA, A, BBB to C, determined on a yearly basis. Assume now that we wish to upgrade a customer from AA to AAA. There are various ways to accommodate the slow or yearly change in a data warehouse environment based upon whether you want to store no historical, full historical, or partial historical information. The first approach is to simply overwrite the old segment value with the new one as you can see here. Obviously, this implies a lot of information since no history of changes is kept. This approach can, however, be used to correct data errors or when the original value is no longer relevant. The second approach stores the historical information by duplicating the record and adding start date, end date, and current flag attribute types as you can see here. a new surrogate key value is introduced, 1, 2, 3, 4, 5, 7 in our case, and both tuples share the same value for the business key, ABC 1, 2, 3 in our case. This clearly illustrates the benefit of using surrogate keys, since we now have two tuples referring to the same customer as indicated by the same business key, customer number, but that can still be distinguished by the surrogate key. The start date and end date attribute types are assigned default values of 31, 12, 9999, but can be updated as needed. Both indicate the so-called validity range, or the time frame during which the other attribute types of the tuple are valid. The most recent tuple has its current flag indicator set to yes or Y. This allows for a quick retrieval of the most recent information of a customer. This method works well if the dimension table is relatively small and the changes are not that frequent. The fact table refers to the dimension table by means of the surrogate key, so each fact will always be related to the correct version of the customer or with the segment value as it was at the moment of the fact. In this way, full historical information is retained. A third approach is to add a new attribute type to the table, as you can see here. In this approach, only partial historical information is stored, since it only keeps the most recent and previous value. The approach can be easily extended by also adding a date attribute type indicating when the most recent change, for example the update to AAA, took place. Also, caution is required not to draw any erroneous conclusions during analyses due to the loss of the full historical information. A fourth approach is to create two-dimension tables, customer and customer history. Both are linked to the fact table using their surrogate keys, but the former has the most recent information, whereas the latter contains the full history of updates, as you can see illustrated here. Depending upon the type of information needed, most recent or historical, the right dimension table is selected. A rapidly changing dimension is a dimension that changes rapidly and regularly over a period of time. Let's now say that a customer status gets updated on a weekly rather than yearly basis based upon how much he or she purchased. Suppose we would like to keep the entire history of changes, then both approaches 2 and 4 discussed in the previous section will result into a lot of rows being added to the dimension table, either customer or customer history, which may seriously hamper the performance. A better alternative might be to first split all customer information into stable, for example gender, marital status, and rapidly changing information, for example segment. The latter can then be put into a separate so-called mini-dimension table, for example customer segment, with a new surrogate key, for example segment key. To successfully make the connection between the customer and customer segment dimensions, we can pursue two options. The first is by using the fact table as a connector. More specifically, we put an additional foreign key in the fact table referring to this mini dimension, as you can see here. As such, the fact table implicitly stores the historical information about the volatile customer data. Note that the customer segment can then only be updated when a new row is added to the fact table, or for example, when a new purchase is made. Additionally, as illustrated, it is also possible to include a foreign key in the customer dimension referring to the current segment in the customer segment mini dimension. This in contrast to the foreign key in a table, which refers to the customer segment at the moment of the fact. Here you can see this illustrated with some example tuples. You can see that the current segment of customer Bart with customer key 1000 is B with segment key equals 2, whereas the segment at the time of the most recent fact was C with segment key 3. Also for SEPA, there is a difference. A is the most current segment, whereas it was D for his most recent fact. For Wilfried, the current segment is A, which is similar to the segment for his most recent fact. Another alternative to connect both tables is by introducing an additional table, customer segment, which includes both surrogate keys, together with the start date and end date attribute types, as you can see here. Whenever a customer segment needs to be updated, a new row can be added to the customer segment dimension table, essentially leaving all other tables unaffected. This allows us to keep full track of the rapidly changing dimension values while at the same time minimizing the storage requirements and safeguarding the performance. Note that customer segment in this way embodies a many-to-many relationship type between customer and customer segment. Once the data warehouse has been designed, we can start populating it with data from the operational sources. During this step, data will be extracted from the source systems, transformed to fit the data warehouse scheme, and then loaded into the data warehouse. Hence, this is commonly referred to as the ETL step. This is not an easy step, since many of the operational sources may be legacy applications or unstructured data that have been rather poorly documented. Some estimates state that the ETL step can consume up to 80% of all efforts needed to set up a data warehouse. It is also an iterative process, which should be executed at regular points in time, for example, daily, weekly, monthly, depending upon the tolerable data latency and/or desired refreshing frequency in terms of the impact on source system performance. Let me do that again. It is also an iterative process which should be executed at regular points in time, for example, daily, weekly, monthly, depending upon the tolerable data latency and/or desired refreshing frequency in terms of the impact on source system performance. To decrease the burden on both the operational systems and the data warehouse itself, it is recommended to start the ETL process by dumping the data in a so-called staging area where all the ETL activities can be executed as illustrated in the figure. Note that the staging area cannot be used for any end-user queries or reporting. It is just an intermediate storage environment for the sake of transformation. The extraction strategy can be either full or incremental. In the latter case, only the changes since the previous extraction are considered, which is also called changed data capture or CDC. Although this is a more efficient approach, it assumes the data in the source systems can be flagged for updates, which is often not possible since many of these operational systems have been carefully optimized and operate in a closed box environment, hereby not allowing any intrusion. During extraction, it is important to properly accommodate the different types of data sources, operating systems, and hardware environments from where the data is sourced. The transformation usually entails the following activities: formatting, cleansing, aggregation and merging, and enrichment. Formatting rules specify how data should be consistently and uniformly encoded in the data warehouse. Cleansing will get rid of some of the inconsistencies or irregularities in the data. Examples are dealing with missing values or handling impossible values such as birth date is 01/01/1000. It is not uncommon to find multiple records referring to the same entity in the operational data sources. This could be due to the usage of different attribute names such as customer idea, cust idea, client idea, or data entry mistakes. These should then be properly aggregated and merged before entering the data in the data warehouse. Finally, the data can also be enriched by adding derived data elements or external data. A straightforward example is calculating the age of a customer based upon the birth date. Another example is enriching customer data with demographical information obtained from an external data provider. During the loading step, the data warehouse is populated by filling the fact and dimension tables, hereby also generating the necessary surrogate keys to link it all up. Dimension rows should be inserted or updated before the fact rows can refer to them. Obviously, all decisions made during the ETL process should be carefully automated and documented to facilitate both maintenance and understanding of the data. An important aspect of this documentation is the generation of metadata about the data structure and its meaning. This information can then be persisted in a metadata repository or catalog. A data mart is a scaled-down version of a data warehouse aimed at meeting the information needs of a homogeneous small group of end users, such as a department or business unit, for example, marketing, finance, logistics, HR, etc. It typically contains some form of aggregated data and is used as the primary source for report generation and analysis by this end user group. There are various reasons for setting up data marts. First of all, they provide focused content, such as finance, sales, or accounting information in a format tailored to the user group at hand. They also improve query performance by offloading complex queries and therefore workload from other data sources, for example, a data warehouse. Depending upon the source of the data, a distinction can be made between dependent and independent data marts. Dependent data marts pull their data directly from a central data warehouse, as you can see illustrated here. Independent data marts are standalone systems drawing data directly from the operational systems, external sources, or a combination of both, as you can see illustrated here. A disadvantage of a physical data warehouse or data mart is that both consume physical storage and must be updated periodically. Hence, they never contain the most recent version of the data. One approach to deal with this is by using virtualization. The idea here is to use middleware to create a logical or virtual data warehouse, sometimes also called a federated database, or virtual data mart, which has no physical data but provides a uniform and consolidated single point of access to a set of underlying physical data stores. In other words, the data is left in its original source and is only accessed or pulled at query time. Because no data is stored or replicated physically, the risk of inconsistent or outdated data is not an issue when working with a virtual data warehouse or virtual data mart. A virtual data warehouse can be built as a set of SQL views directly on the underlying operational data sources, as you see here. A virtual data warehouse can also be built as an extra layer on top of a collection of physical independent data marts, as illustrated here. A virtual data warehouse should provide a uniform and consistent metadata model and data manipulation language, such as SQL. The metadata model contains the scheme mappings between the schemes of the underlying data stores and the scheme of the virtual data warehouse. Queries are then reformulated and decomposed using these scheme mappings on the fly, whereby the underlying data is fetched and consolidated on demand. This provides the queries with a real-time perspective on the underlying evolving data. In this figure, the wrappers are dedicated software components which receive queries from the upper level, execute them on the underlying data store, and convert the result to a format, for example relational tuples, that can be understood by the query processor. A virtual data mart is usually defined as a single SQL view. The view can be directly defined on physical operational source data, in which case we have a virtual independent data mart, or on a physical or virtual data warehouse, in which case we have a virtual dependent data mart. Since multiple virtual data marts may share data, it is important to carefully think about how the views are defined in order to facilitate the overall maintenance. A disadvantage of virtualization is that it requires extra processing capacity from the underlying operational data sources. Hence, it should only be considered in case the number of reports or queries is rather limited. The performance of the latter may then be optimized by using intelligent caching mechanisms and cache indexes combined with materializing some of the views to speed up data access. Furthermore, it is not possible to keep track of historical data, since old data is typically replaced by new data in the underlying data sources. An operational data store, or ODS for short, is another way of dealing with the disadvantage of data warehouses not containing up-to-date data. To put it simply, an ODS can be considered as a staging area that provides query facilities. A normal staging area is only meant for receiving the operational data from the OLTP sources for the sake of transforming the data and loading it into the data warehouse. An ODS also offers this functionality, but in addition, it can be queried directly. In this way, analysis tools that need data that is closer to real time can query the ODS data as it is received from the respective source systems before time-consuming transformation and loading operations. The ODS then only provides access to the current, fine-grained, and non-aggregated data which can be queried in an integrated manner without burdening the OLTP systems. However, more complex analyses requiring high-volume historical and/or aggregated data are still conducted on the actual data warehouse. In some configurations, the ODS and data warehouse together are overlaid with a virtualization layer, providing a single access point for queries on combined near real-time and historical data. Note that the operational data store is still part of the data warehouse setup and not to be confused with the actual operational source systems. Much more recent than data warehouses, the data lake concept became known as part of the big data and analytics trend. Although both data warehouses and data lakes are essentially data repositories, there are some clear differences, as you can see listed here. A key distinguishing property of a data lake is that it stores raw data in its native format, which could be structured, unstructured, or semi-structured. This makes data lakes fit for more exotic and bulk data types that we generally do not find in data warehouses, such as social media feeds, click streams, server logs, sensor data, etc. A data lake collects data emanating from operational sources as is, often without knowing upfront which analyses will be performed on it, or even whether the data will ever be involved in analysis at all. For this reason, either no or only very limited transformations, such as formatting and cleansing, are performed on the data before it enters the data lake. Consequently, when the data is tapped from the data lake to be analyzed, quite a bit of processing will typically be required before it is fit for analysis. The data scheme definitions are only determined when the data is read, scheme on read, instead of when the data is loaded, scheme on write, as is the case for a data warehouse. Storage costs for data lakes are also relatively low because most of the implementations are open source solutions that can be easily installed on low-cost commodity hardware. Since a data warehouse assumes a predefined structure, it is less agile compared to a data lake which has no structure. Also, data warehouses have been around for quite some time already, which automatically implies that their security facilities are more mature. Finally, in terms of users, a data warehouse is targeted towards decision makers at middle and top management level, whereas a data lake requires a data scientist, which is a more specialized profile in terms of data handling and analysis. The ultimate goal of setting up a data warehouse is to provide new insights for both tactical and strategic decision making. The term business intelligence, or BI, is often referred to as the set of activities, techniques, and tools aimed at understanding patterns in past data and predicting the future. Since data is the key ingredient to any BI application, it is important that it is appropriately stored, managed, and of good quality. This is often referred to as the garbage in, garbage out principle, stating that bad data gives bad insights, which in turn leads to bad decisions. That's why we started this chapter by extensively discussing the data warehouse architecture. Note that although this is not a strict requirement, most BI systems are built upon an underlying relational data warehouse. Various BI techniques can be used to extract patterns and provide new insights and data. Each of them differs in terms of sophistication, complexity, and computing resources needed. In what follows, we discuss query and reporting, pivot tables, and OLAP. Query and reporting tools provide a user-friendly graphical user interface, GUI, where the business user can graphically and interactively design a report. It is important to stress that it is not an IT expert doing the query and reporting, but a business user. Therefore, this approach is sometimes also referred to as self-service BI. Hence, the building blocks of the reports should preferably refer to business terms rather than technical IT artifacts such as database tables, views, indexes, etc. Some tools provide an intermediate query by example QBE facility that sits in between the database and the business concepts. The idea is that a query is composed in a user-friendly way by visualizing database tables, whereby the business user can enter conditions for each field that needs to be included in the query. This can then be translated to a formal data manipulation language such as SQL. Once the report has been designed in terms of format and content, it can be refreshed at any time with up-to-date information from the underlying data store. Query and reporting tools implement innovative visualization techniques aimed at making interesting data patterns stand out more prominently. A pivot or cross table essentially cross-tabulates a set of dimensions in such a way that multidimensional data can be represented in a two-dimensional tabular format. You can see an example illustrated here, where the dimensions region and quarter are summarized in terms of aggregated sales. Note that a pivot table also contains row and column totals as depicted. The measurement data can be aggregated in various ways, such as in terms of count, sum, average, maximum, minimum, etc. BI tools also provide various user-friendly graphical facilities to customize the pivot table by dragging and dropping dimensions of interest. The first straightforward action is pivoting, hence the name, whereby rows and columns are rotated according to the business user's preference. Also, drill down facilities are provided, whereby either a dimension is further deaggregated into more detail, for example, splitting up America into North America and South America in our example, or new dimensions are added, for example, adding product in our example. The idea here is to navigate from coarse to fine granularity to better see where interesting patterns may originate. Removing dimensions, or roll up, is also supported. In our example, we may want to roll up the region dimension in order to get the full picture of sales across all quarters. On-Line Analytical Processing, OLAP, allows you to interactively analyze the data, summarize it, and visualize it in various ways. The term online refers to the fact that the reports can be updated with data almost immediately after they have been designed or with negligible delay. The goal of OLAP is to provide the business user with a powerful tool for ad hoc querying. The key fundament of OLAP is a multidimensional data model, which can be implemented in various ways. In what follows, we discuss MOLAP, multidimensional OLAP, ROLAP, relational OLAP, and HOLAP, hybrid OLAP. Multidimensional OLAP, MOLAP, stores the multidimensional data using a multidimensional DBMS, MDBMS, whereby the data is stored in a multidimensional array-based data structure optimized for efficient storage and quick access. The dimensions represent the index keys of the array, whereas the array cells contain the actual fact data, for example sales. Aggregates are pre-computed and also physically materialized. This is illustrated here, where a two-dimensional array or matrix represents the sales for different products across different quarters. The element at row 2, column 3 of the array represents the sales of product B during quarter Q3. Note also that totals have been pre-computed and stored in the array. The element at row 4, column 5 represents the total sales of product D across all quarters, whereas the element at row 5, column 5 represents the overall sales of all products across all quarters. A potential problem with this storage approach is that the array may get sparse with many zeros if only a limited number of combinations of dimension values occur. Ideally, an MDBMS should provide facilities for handling these sparse datasets efficiently. Although MOLAP can be fast in terms of data retrieval, it needs more storage to accomplish this. Moreover, it scales poorly when the number of dimensions increases. MDBMSs make use of proprietary data structures and data manipulation languages, DML, so no universal SQL-like standard is provided for data handling, which impedes their adoption. Furthermore, they are not optimized for transaction processing. Updating, inserting, or deleting data is usually quite inefficient. Finally, they are typically not very portable because of their tight integration with particular BI tools. Relational OLAP, ROLAP, stores the data in a relational data warehouse, which can be implemented using a star, Snowflake, or fact Constellation scheme. The advantage of this is that RDBMSs have been much better standardized and provide SQL as a universal data manipulation language. If it is feasible in terms of workload and performance, the same RDBMS can be used for both OLTP and OLAP applications. Furthermore, ROLAP scales better to more dimensions than MOLAP. The query performance may, however, be inferior to MOLAP unless some of the queries are materialized or high-performance indexes are defined. Hybrid OLAP tries to combine the best of both MOLAP and ROLAP. An RDBMS can then be used to store the detailed data in a relational data warehouse, whereas the pre-computed aggregated data can be kept as a multidimensional array managed by an MDBMS. The OLAP analysis can first start from the multidimensional database. If more detail is needed, for example during drill down, the analysis can shift to the relational database. This allows you to combine the performance of MOLAP with the scalability of ROLAP. Various OLAP operators can be used to interactively analyze the data and look for interesting patterns. In what follows, we illustrate them using the cube displayed here. This cube has 3 dimensions: product, region, and quarter. The data in the cells represent the sales corresponding to each combination of dimension values. Roll-up or drill-up refers to aggregating the current set of fact values within or across one or more dimensions. A distinction can be made between a hierarchical and a dimensional roll-up. The former aggregates within a particular dimension by climbing up the attribute hierarchy. For example, going from day to week to month to quarter to year, whereas the latter aggregates across an entire dimension and then drops it. The figure shows the result of a dimensional roll-up of the time dimension, which can then be further rolled up across region as well as illustrated. The reverse process is referred to as roll down or drill down. The idea is to deaggregate by navigating from a lower level of detail to a higher level of detail. Again, a distinction can be made between hierarchical roll down, for example going from year to quarter to month to week to day, and dimensional roll down in which a new dimension is added to the analysis. Drill across is another OLAP operation whereby information from 2 or more connected fact tables is accessed. Consider our earlier fact constellation scheme with 2 fact tables, sales and shipper. Adding shipper fact data to an analysis on sales fact data is an example of a drill across operation. Slicing represents the operation whereby one of the dimensions is set at a particular value. This is illustrated here, where a slice is taken representing the sales in the second quarter for all products and regions. Both horizontal and vertical slicing are possible. Dicing corresponds to a range selection. Dicing corresponds to a range selection on one or more dimensions. In this figure, a dice is selected corresponding to the sales of products B and C in quarters 2 and 3 in Europe. To facilitate the execution of OLAP queries and data aggregation, SQL99 introduced 3 extensions to the group by statement: the cube, rollup, and grouping sets operator. The cube operator computes a union of group bys on every subset of the specified attribute types. Its result set represents a multidimensional cube based upon the source table. Consider the sales table depicted here. We can now formulate the SQL query shown here. Basically, this query computes the union of 2 to the power 2 or 4 groupings of the sales table, being quarter region, quarter region, and an empty group list representing the total aggregate across the entire sales table. In other words, since quarter has 4 values and region 2 values, the resulting multiset will have 4 times 2 plus 4 times 1 plus 1 times 2 plus 1 or 15 tuples. Here you can see those 15 tuples. Null values have been added in the dimension columns quarter and region to indicate the aggregation that took place. They can be easily replaced by the more meaningful all if desired. More specifically, we can add the statement to the right of my slide to the select clause of the SQL query. The grouping function equals 1 in case a null value is generated during the aggregation and 0 otherwise. This distinguishes the generated nulls and the possible real nulls stemming from the data. We will not add this to the subsequent OLAP queries so as to not unnecessarily complicate them. Also observe the null value for sales in the 5th row. This represents an attribute combination which is not present in the original sales table, since apparently no products were sold in Q3 in Europe. Remark that besides some, also other SQL aggregator functions such as min, max, count, and average can be used in the select statement. The rollup operator computes the union on every prefix of the list of specified attribute types from the most detailed up to the grand total. It is especially useful to generate reports containing both subtotals and totals. The key difference between the rollup and cube operator is that the former generates a result set showing the aggregates for a hierarchy of values of the specified attribute types, whereas the latter generates a result set showing the aggregates for all combinations of values of the selected attribute types. Hence, the order in which the attribute types are mentioned is important for the rollup, but not for the cube operator. Consider the following SQL query at the top of my slide. This query generates the union of 3 groupings: quarter and region, quarter, and the full aggregation. The resulting multiset will thus have 4 times 2 plus 4 plus 1 or 13 rows. You can see the 13 rows displayed here. You can see that the region dimension is first rolled up, followed by the quarter dimension. Note the 2 rows which have been left out when compared to the result of the cube operator. Whereas the previous example applied the group by rollup construct to to 2 completely independent dimensions, it can also be applied to attribute types that represent different aggregation levels, and hence different levels of detail, along the same dimension. For example, suppose the sales table tuples represented more detailed sales data at the individual city level and that the table contained 3 location-related columns: city, country, and region. We could then formulate the following roll-up query, yielding sales totals respectively per city, per country, per region, and the grand total. Select region, country, city, sum sales from sales table, group by roll-up, region, country, city. The grouping sets operator generates a result set equivalent to that generated by a union all of multiple, simple group by clauses. Consider the following example. Select quarter, region, sum sales from sales table, group by grouping sets, quarter, region. This query is equivalent to select quarter, null, sum sales from sales table, group by quarter, union all, select null region sum sales from sales table, group by region. You can see the result displayed here. Multiple cube, roll-up, and grouping set statements can be used in a single SQL query. Different combinations of cube, roll-up, and grouping sets can generate equivalent result sets. Consider the following query. Select quarter, region, sum sales from sales table, group by cube, quarter, region. This query is equivalent to select quarter, region, sum sales from sales table, group by grouping sets, quarter, region, empty set. Likewise, the following query, select quarter, region, sum sales from sales table, group by roll-up, quarter, region, is identical to select quarter, region, sum sales from sales table, group by grouping sets, quarter, region, empty set. SQL 2003 introduced additional analytical support for 2 types of frequently encountered OLAP activities: ranking and windowing. Ranking should always be done in combination with an SQL order by clause. Assume we have the table depicted here. Various ranking measures can now be calculated by using the SQL query you see illustrated here. The result of this query is depicted here. The rank function assigns a rank based upon the ordered sales value, whereby similar sales value The rank function assigns a rank based upon the ordered sales value, whereby similar sales values are assigned the same rank. Contrary to the rank function, the dense rank function does not leave gaps between the ranks. The %rank function calculates the percentage of values less than the current value, excluding the highest value. It is calculated as rank minus 1 divided by number of rows minus 1. The comDist function calculates the cumulative distribution, or the percentage of values less than or equal to the current value. Windowing allows calculating cumulative totals or running averages based on a specified time window. In other words, windowing allows getting access to more than one row of a table without requiring a self-join. Consider the table shown here. This query calculates the average sales for each region and quarter on the basis of the current, previous, and next quarter. Here you can see the result. The partition by region statement subdivides the rows into partitions, similar to a group by clause. It enforces that the windows do not reach across partition boundaries. In other words, the sales average values will always be computed within a particular region. As an example, the sales average value for quarter 2 in America will be calculated as 10 plus 20 plus 10 divided by 3 equals 13.33. Whereas for quarter 4 in America, it is calculated as 30 plus 10 divided by 2, or 20. In this chapter, we introduce data warehousing as an essential component to build enterprise-wide business intelligence or BI solutions. We extensively zoomed into various types of data warehouse schemas. And modeling specifics, and also reviewed various issues related to their development. We discussed data marts, the important topic of virtualization, and contrasted data warehouses with data lakes, hereby clearly stating that both technologies are complementary rather than substitutes. The second part of this chapter zoomed into business intelligence. More specifically, we covered query and reporting, pivot tables, and on-line analytical processing, or OLAP. It is important to note that these BI techniques are verification-based, since they heavily depend upon input provided by the business user to find interesting patterns or test hypotheses. If you want more information, we are happy to refer to our book, Principles of Database Management. You can find more information on the website at the bottom of my slide.